So today we will start with the third part of this chapter. Okay, we will see how to compute linear maps. Okay, and so we will do part A, representing linear maps with matrices. Representing linear maps with matrices. In the previous chapter, we have seen how to represent a vector with respect to a basis. Okay, so we are going to use that concept. So even if you don't know how to represent a matrix with a vector with respect to a basis, in the tutorial, in the next video, I will do a tutorial about what we are covering in this video. Okay, and I will do a quick review of how to represent a vector with respect to a basis. Okay, so we continue. Let's start with the definition. Definition. Okay, so we will suppose that V and W are vector spaces of dimension or dimensions n and m with basis B and D, or I can just say basis. So B is the basis for V and D is the basis for W, or I should say respectively. Okay, respectively. And we are going to suppose that homomorphism or a linear map. Okay, homomorphism is the same as a linear map. Defined from V to W is okay, a linear map. Linear map. So this is going to be a very long definition. Okay, if the representation of with respect, go a little bit lower. So if the representation with respect to D, with respect to the codomain basis of the images of the vectors of the domain basis, okay, that's a very long sentence, but hey, let me write it. Okay, the representation with respect to D of the images of the vectors of the basis P is equal to, okay, H1 1 H2 1 H M1. Okay, so that's the representation with respect to D of the image of the first base, of the image of the first vector of the basis P Okay, dot. Okay, and the representation with respect to D of the last vector, beta n equals h1 n h2 n hm n. Okay, so if that is the representation, if you remember from a previous video, okay, we have seen what characterizes a homomorphism. A homomorphism is characterized by its action on the basis. That's a very important theorem to remember, okay? So once we have represented with respect to D the images of the vectors of the domain basis, then the definition says then just concatenating these representations are the matrix representation of the entire linear map. Okay, then um, the representation, let me write it, representation with we write it with respect to BD, the domain basis and the codomain basis of the map, of the linear map, is H1, 1, H2, 1, HM1, okay, and here is a H, so we just concatenate all these representations together. H21, H12, 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 H22, H2, HM2, M2. So that's the representation of the image of the second vector of the domain basis. Dot 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 H1 n H2 n, okay, H M n. So this matrix B D, or we can instead of writing rep BDH, we can also write it as square brackets H B D, or some authors write it H B D. Okay, it doesn't matter. So this matrix we have just written is then is the matrix representation matrix representation of H, sorry, of H with respect to the basis B D. Okay, so this matrix. Is that okay? So in the next video, I will show step by step how to find the matrix representation, okay, or I can just give you, yeah. First of all, we need a domain basis. Then we need to find the images of those, the element of the element of that domain basis. and then represent those images with respect to the basis of the codomain space. Is that okay? We will do a tutorial short. So let me continue. Here, that's a note. Let me give you a note. So from the above definition, okay, a note. So from the above, from the above or previous definition on the previous slide, the above definition, okay, the number, the number the number of columns is the dimension of the map, dimension of the map. Of the maps. Okay, what am I writing? Is the dimension of the maps domain. Okay, while the number of rows, okay, is the dimension of the maps codomain. Of the maps codomain. Okay, so let's continue. This is going to be a big theorem, so let me go to next page, okay? Theorem. Here again, we are going to assume two vector spaces. Assume that V and W are vector spaces of dimensions M and M. Okay, dimensions N and M. Let me be sure. Okay, of dimension N and M, yeah, I got it right. Of the dimensions M and N with basis B and D, respectively, of course, okay? Respectively. And you're going to suppose that the map H is defined from V to W is linear. Okay, so if H is represented if H is represented by the matrix we have seen a while ago in the definition is represented by the following matrix: H1, 1, H21, HM1. Okay. H1, 2, H22, HM2, sorry, H1N, H2N, HMN. Okay. If the map is represented by this matrix and also a vector, okay, V is represented by, okay, let me write here BD. Sometimes we can ignore it, but it's good to write it. So if the vector V from the domain space is represented by C1, C2, C, N, then the representation, then the representation of the image of V in, okay, is the representation of the image of V is the following matrix, okay, is the matrix is the following matrix. PD of the image of V. Okay, so we are going to multiply a matrix by a vector actually, but I want to write it here. I will do it in the next video. So basically it's actually from the theorem that we derive the definition of multiplying a matrix with a vector. Okay, so the theorem says that the matrix representation is going to be H1, 1, C1 plus H1, 2, C2 plus H1, N, C, and this theorem is easy to prove, but as I said, I won't do too much proof here in the lecture, but if anyone needs a formal proof, just email me and I will record a short video for the proof. Okay. H21 C1 plus H22 C2 plus H2 and Cn. Okay. Dot. hm1 m1 c1 plus hm2 c2 plus hm n cn. Okay, so that's the theorem. Is that okay? So that's how we are going to represent the image of a vector with respect to the codomain basis. Now I will, so from this theorem you can derive yourself the definition for a matrix, multiplication of a matrix with a vector. Okay. So definition. Okay, so the matrix vector product okay, so the matrix vector product of m by n matrix and n by 1 vector is, so as you can see in the definition, the dimension of the codomain of the matrix the number of rows is the dimension of the number of rows is the dimension of the codomain, and the number of column is so this is a row column. So the dimension, the number of column is the dimension of the domain. Okay, so domain, codomain. Oh, basically, let me not complicate things. So basically, the number of columns of the matrix should be the number of rows of the vector. Okay, to be able to multiply a matrix by a vector. So let's continue our definition. So we are saying that the matrix vector product of m by n matrix and n by 1 vector is defined as follows. So we have our matrix A1 1, A2 1, AM 1, A1 2, A2 2, AM 2, A1 N, A2 N, AM N. Okay, so this is our matrix with n m rows and n columns, m rows and n columns multiplied by our vector c1, c2, cn. This is going to be, so you multiply the rows, we do dot product of the rows of the matrix with the column of the vector. So we pick that row, multiply by that column, okay? Component-wise multiplication. Okay. So this is going to be, so we have A1, 1 multiplied by C1, A1, 1 multiplied by C1 plus A2, 2, sorry, A1, 2, that's 1, 2. A1, 2 multiplied by C2 plus A1n multiplied by Cn. 1n multiplied by Cn. We do the same for the second row. Okay, so A21 multiplied by C1 plus A22 multiplied by C2 plus A2n multiplied by Cn. Okay, and we do that for the last row as well. Amn multiplied by C1 plus M2 multiplied by C2 plus Amn multiplied by Cn. Okay. Put the dots here. So that's how we define a matrix vector product. Okay. So I think I'm going to stop the lecture here, and in the next video we will do the tutorial. Okay, thanks.